Hi, I'm Takahiro Sumi from Osaka University. I'm going to talk about a free-floating planet mass function by the microlensing. So here's the schematic of the microlensing. There is the lensing object along the line of sight towards the background stars. The light from the star is bent like this and then magnified. And when the lens is passing along crossing the line of sight, the magnitude of the star is magnified like this instantaneously, and then going back to the normal brightness. And the time scale of this event is scaled as the Einstein time scale. And this is the only observable for the microlensing in general. And this is the angular Einstein radius divided by the proper motion. In this time scale, the mass, distance, and transverse velocity of the lensing object is degenerated. And, this is the proportional to the square root of the mass. And then if the time scale is less than 1 day, this is most likely the planetary mass object, even though we cannot directly measure the mass in general. So if we found a short timescale microlensing event, this is very likely the planetary mass object. So the observation by the MOA collaboration during the 2 years, we found about 10 short timescale events with timescale of the less than 2 days. So here is the one example. The light calls for 2 years. There is only one magnification during the 2 years. And here is a close-up. The time scale is about 1 day, 1.2 days. So this is very likely the Jupiter mass. So as I said, we cannot measure directly the mass of the lens object. We have to do statistical analysis. So here is the time scale distributions. And the most of the time scale longer than 1 day can be explained by the known object, like a brown dwarf, main sequence, white dwarf, neutron star, and black hole. But there is some excess at the short time scale. So we first try to explain this excess by introducing the planetary mass population. So even though this analysis have a very large uncertainty, is limited by the small number of the statistics, later, Ogle updated this similar analysis with their larger statistics with high quality light curves. So here is their timescale distributions. Even though they couldn't find the excess at around 1 day, but they found some excess at even shorter timescale, about 1.2 days. So that may indicating that there is even smaller planetary mass population, indicating the planetary mass population with the super Earth. So as I said, the microlensing itself, we can measure only the time scale, not the mass. But if we can measure the finite source effect, we can measure the Einstein radius, angular Einstein radius, theta e. So if the lens directly passes the surface of the source plane, the magnification is surplus. Here is some example. If there is no finite source effect, the magnification is very steep and high. But if there is an effect of the finite source size, the magnification is marginalized, and then duration is longer. This duration is basically the time of the crossing on the surface of the source. So this apparent time scale is the angular source radius divided by the proper motions. So in the microlensing fit, we can measure this finite source parameter called rho. And this is the source radius divided by the angular Einstein radius. This source radius can be measured from the color and the magnitude of the source. Then we can derive this angular Einstein radius. So because one of the degeneracy is broken by this, the angular Einstein radius is more good indicator for the mass of the lens system. And if that is smaller than 10 micro-arcsecond, this is most likely the planetary mass. So the many microlensing survey like KMT, OGO, and more detecting such events with short time scale events with finite source effect. Here is some example. This Einstein angular size is theta E is 9 micro-arcsecond. This is the 2 micro-arcsecond and the 4 micro-arcsecond. So these are very likely the planetary mass. And this is the extremely one. The theta E is 0.8 micro-arcsecond. So the probability mass is terrestrial mass. So this is the first terrestrial mass free-floating candidate. And then later, Gould et al. Published the distribution of the theta E of the 30 events with finite source effect from the KMT net. And they found there is a deficit of the events, something around theta E is around 10 micro-arcsecond. So they indicating that there is the distinct planetary mass population around here, which is clearly separated from the brown dwarf object like this. So this study is only focused on the theta E analysis, and the previous studies use only the timescale distributions. So both have information on the planetary mass object. So that it's wasting just only either timescale or theta E. So we try to next step is try to make use of both timescale and also the theta E as well. So for this analysis, we make use of the 9 years of the MOA project. The MOA is the microlensing observation in astrophysics, collaboration between Japan, New Zealand, and the United States, observing at the Mount John Observatory in South Island of the New Zealand. We are using 1.8 meter telescope with the 80 megapixel camera. We have a very wide 2.2 square degree field of view. Because of that, we can conduct fast high cadence microlensing survey observations. Here is our field of view, the Galactic Center disks. We are observing around 50 square degree, including 20 million stars. In the red field, we are observing with 15 minutes cadence, and the blue is 47 minutes, and then other fields are 95 minutes cadence. We are detecting about 600 events every year. So that high cadence makes us possible to detect such a short timescale microlensing event. So the observed images are reduced real time by the difference imaging analysis, and then finding the many variable objects, and then selecting only the microlensing event from the removing the periodic variable star and the various artifacts. So to look for the short timescale event, there are many artifacts, especially for the astronomical artifacts. The one is the short binary events. Here is the clear crossing signal. The timescale is less than 1 day, but it looks like a very clear cusp crossing, so we can differentiate from the single lens event. And here is the very short caustic event with caustic entrance and exit. So by modeling this event, we can remove this artifact compared to the single lens event. So the other even more severe background is the CV or flare stars. Here's an example. They are mostly the fast rise and slow decline, and sometimes repeat. So if we try to fit with the microlensing light curves, that give us physical parameters. By using that information, we can remove these artifacts. And also another significant artifact is the moving object. If we do the photometry on the fixed position for the new object, then if that object is moving, that creates this kind of the symmetric light curves with short time scale. And this one also give us the physical microlensing parameters, so we can remove this object. Then after we analyzed the 9 years of the MOA data, we found 6,000 microlensing events. But we selected only the 3,500 high quality events. In this sample, we found 12 events with time scale of less than 1 day. And in this, 6 of them are time scale of less than 0.5 days. So these are the planetary mass of the candidate. And in this sample, we found 13 events with finite source effect. So we could measure the theta E, angular Einstein radius. Then we can measure this theta E from this object. So here is some sample light curves with the time scale of less than 1 day. The top panel showed the light curve of the 9 years to make sure there is only one brightening episode. The flare sometimes repeating. So this is the clear microlensing signal. And the middle panel showed a close-up view. The most of the time scale is less than 1 day per entry. And the bottom panel indicating the residual from the best fit single lens model. Another one, here you can see the clear finite source effect, and we could see we measured the theta E. Here is another event, and this one also have a finite source effect. So here's the 2 events which we could find the finite source effect in the short time scale. So this one, the theta E is 4 micro-arc second. So the inferred mass by the Bayesian analysis is 22 Earth mass. So it's likely the Neptune mass. And here is the theta E is 0.9 micro-arc second. So it's very small. So the inferred mass is either 0.4 or 0.7 Earth mass, depending on the assumed power or mass function for the planetary mass object. But in either cases, this is the sub-terrestrial mass object. So this is the second case for such a small terrestrial mass object after Auger event. So here is the cumulative distribution of the theta E compared to the Auger et al. Result by the ChemTNet. The red is our result, and black is the Auger et al. And as you can see, we also see some deficit of the event at around 10 micro-arc second. So we confirmed there is the distinct population of the planetary mass object compared to the Browndorf object. And this blue indicating the position of the terrestrial mass found by the Auger. And here is one of our candidates. This is the second case, which confirming that there is really existing such a terrestrial mass planetary mass object. So to do the statistical analysis using both time scale and also the theta E, we conducted image level simulation with finite source effect to measure the detection efficiency. So we put artificial events on the real observed difference imaging of our data set with various parameters of the microlensing, including the parameter for the finite source effect with the theta star and the theta E. And then measure how much event we can recover. So here is the result. Here is the first measurement of the 2D detection efficiency as a function of the TE and the theta E. So as you can see, there are the fewer detection, smaller detection efficiency at the short time scale as usual, but you can see there is a limit of the detection efficiency as around 10 to minus 3. This is because of the finite source effect. And here is the 1D projection of this analysis into the time scale. And this dotted line indicating the detection efficiency without finite source effect. But with the finite source effect, this red curve indicating this is reduced at the short time scale because of the finite source effect. So we're going to use this 2D detection efficiency for the short time scale event, but for the longer time scale event, we're going to use this 1D detection efficiency for reduce the calculation time. And then we conducted a likelihood analysis to fitting with the information of the TE and the theta E by using the event rate as a function of the TE and the theta E by using the galactic model by the Koshimoto et al. With the assumed mass function. In the mass function, we adopted a power law mass function like a Kuropa model for the stars and the brown dwarf with power of the alpha 3 for the brown dwarf. And then we added another power law for the planetary object with the power law index of the alpha 4 with normalization Z. And here is a corner plot of this, the fitting. And we found the best fit power law is 0.96. So this is the best fit time scale distributions. You can see the time scale longer than 1 day can be explained by the brown dwarf and the main sequence, white dwarf, neutron star, and black hole. And then there is some excess below the 1 day. And then this green curve is the contribution from this the power law mass function for the planetary mass object. So from this result, we estimated the number of the FFP is about 20 times than the star, assuming if there is the mass function extending to down to the 0.3 Earth mass. So this is the best fit mass function. This blue indicating the mass function, power law mass function of the star and the brown dwarf, and the green indicating new planetary mass population. The shaded region indicating the 1 sigma uncertainty, and this orange shade is for the case of the assuming the broken power law for the planetary mass. And that is we recognize as the conservative uncertainty for the mass functions. And gray indicating the mass function for the cold bound planet by microlensing. So by comparing this, we found, from this power, we can see that there are more low mass planets down to the Earth mass FFP than compared to the heavier object like this. And comparing to the bound planet to this, there are more bound planets at the high mass, but fewer bound planets at low mass. And if we fit this bound planet by single power law, we get the power law index of the 0.6. And this, our new result for the point is 0.96 is steeper than this power law index of 0.6. That's indicating the preferring the scenario of these planets formed around the stars originally, and then less massive objects are more likely ejected by the as a FFP. So then from this mass function, we estimated about 19 times more the FFP are more abundant compared to the bound planet. And this is about 6 times more of the all known planet, including the transit planet. So as you know, the Roman can detect FFP as low mass as Mars. From our mass function, we estimated Roman will detect about 1,000 FFP down to the, if we are assuming the down to the 0.1 Earth mass. And half of them are less than the Earth mass object. And then Roman will get more accurate FFP mass functions. And we also built another telescope in South Africa called the PRIME, Prime Focus Infrared Microlensing Experiment. The primary is 1.8 meter. We have a 1.4 square degree field of view with infrared by running the H4RG detector from the Roman project. This will be the first dedicated near-infrared microlensing experiment. We are going to supporting the Roman project by conducting the precursor and also the concurrent observation towards the bulge. So one of the key science of the prime is that we're going to conduct a simultaneous observation with Roman from the ground. And if we observed one event from the space and the ground, we can see the slight difference of the magnification and also the timing of the peak because of the parallax. This is so-called the space-based parallax. And this is the only way to measure the mass of the free-floating planet. And the difference of the distance of the Earth and the L2 is 0.0 AU. And this is suitable for the free-floating planet for measuring this parallax. So the microlensing FFP candidates, we are not really sure they are unbound or distant planet, because microlensing data can only set the lower limit within the 10 AU. So the one way is to try to set a tighter limit or detect a host star for the microlensing FFP candidate by the high resolution deep imaging by the Keck, VLT, Subaru, HST, JWST, and also the Roman itself. This is the simulation by the J. Anderson to try to measure the lens object 6 magnitude fainter than the source star. And this is a very powerful way for constraining whether they are really the distant planet or free-floating. Another way is the measuring the distribution of the wide orbit planet by the various methods. Of course, Roman is very sensitive to the cold Romas planet, as you can see. But still, below the like Neptune mass and then wider than the 10 AU, we expect only a small number of the statistics. And also in this wide planet, we are really not sure whether we can, detect a signal from the host star or not. So we cannot distinguish either the bound planet or free-floating planet in this region. So another way for the constraining the wide orbit is traditionally the near-infrared direct imaging by 8-meter class ground telescope is working. For example, this Gemini Deep Planet Survey put the constraint on like less than 40% of the star have one Jupiter mass planet at 10 to 500 AU. And also the various other survey put a stronger constraint, like less than 60% for the 1 to 13 Jupiter mass at 10 to 1000 AU, or less than 0.6% for the 5 to 13 Jupiter mass for up to the 300 AU. This kind of things. But these kind of deep near-infrared imaging by the current facility, ground-based facility like VLT, Gemini, and Subaru, they are only sensitive for the self-luminous young giants. But still, it's very challenging to finding the low-mass planets by direct imaging. So maybe the TMT may found such an object by the reflected light or thermal light for the smaller mass, and HWO may detect the Earth at the 1 AU at the 10 parsec. So the planet can be detected between the inner and the outer working angle. So the outer working angle of the HWO is about, it's not fixed, but it's about 0.5 second. So the HWO can detect Earth at 1 AU at 10 parsec. But in case of the Earth, it's limited to the about 1 AU or less than 2 AU, not only because of the outer working angle, but its faintness. If we go to the wider, reflected light gets fainter significantly. But Neptune might be bright enough up to the widest outer working angle with reasonable exposure time, like 22 hours at 10 AU of the the Neptune mass object. So the detection, they can detect even wider orbit depending on the inclination and the phase and also the eccentricity. So this paper estimated planet visibility fraction as a function of the stellar distance here. Here the visibility function stands for the portion of the planet's orbit during the it's detectable between the inner working angle and the outer working angle. So this bottom curve, so different curve is the result for the different outer working angle. And the bottom bottom curve indicating for the case of the outer working angle of the 300 mass. And the second one is for the case of the 800 mass. So the HWO is somewhere between these two curves, and probably they can detect these objects like a Neptune down to the Neptune for the 50% of the object in the this up to the system closer to the 23 parsec up to the 30 AU. So astrometry is also the sensitive to the wider planets. The astrometric amplitude for the Earth at 1 AU is 0.3 microarc second, and 3 microarc second for the 10 AU. And it's the higher signal for the Jupiter. So the Gaia can detect giant planets at up to the several AU. And HWO can detect Earth at more than 1 AU. But how wide we can go is dependent on the duration of the observation. If HWO extend to 10 years or 20 years, they can detect wider orbit. But anyway, it is very important to study the geometry, the demographics of the wider orbit in collaboration with the free-floating candidates to really understand the nature of such object. So here's a summary. We first measured the mass function of the FFP by microlensing, and this power law index indicating there are many Earth mass FFP candidates. And this is the 20 FFP per star. And this result indicating they are probably formed around the star and ejected later. And they informed us not only the number of the planets in orbit, but also the planets that formed earlier and scattered. And then Roman will get more accurate FFP mass function. Thank you.
Hi, thanks, Taka. So my name is Kaming. I'm a postdoc at MIT. So I have a question about the likelihood analysis. So you adopted a lower mass cutoff at 0.33 Earth mass, right? Presumably that's related to the like around 1 sigma lower mass limit of the 5919 object. So my question, can you switch back to the 5919 event page, the slide?
Mm-hmm. So the you mean the cutoff?
Can you switch to the 5919 the light curve page or the mass estimate? Yeah, so it looks like the mass could be as high as 2 Earth mass within 1 sigma.
Yeah.
So if you adopted for a likelihood analysis a lower cutoff at 2 Earth mass instead, how would that, because that would be pretty reasonable too. How would that change the total number of FFPs per star? that you estimate?
So we tested the different low mass cutoff, even the higher than this mass, and so I mean excluding this object from the statistical analysis, but the power law doesn't change. So the shape of the power law is mostly determined by the low mass, the high mass objects.
Okay, that's really
they depend on this object.
Okay, that's really interesting. Thank you.
Thank you. Ray Jayawardena, Johns Hopkins. Sorry to ask a bit of a naive question, but it seems fundamental here. If you go to the conclusions slide, I mean, you're talking about 20 plus FFPs per star, which is very different from what those of us who do deep imaging spectroscopy of young star-forming regions find, which is, maybe 20 to 40% FFPs per star. But is the main explanation, you think, that we're just looking at very different populations at rather different mass ranges? Because obviously the direct imaging is sensitive down to maybe a few Jupiter masses, and you're sensitive to way down in mass.
Yeah, direct imaging is mostly for the high mass Jupiter mass object, and this number changes significantly depending on the low mass cutoff for the integrating. So it's changing depending on the how low we extending for the measure the mass function. So mostly the low mass contribution.
So there might be an overlap in mass, but we're really peaking at ultra low masses here.
Yeah.